Assalamu alaikum. Welcome to the next lecture of this electricity in daily use. Today we'll start our topic as superposition. So this theorem, or we can say this statement, or this technique is used when a circuit has two or more independent voltage or current sources, or in general two or more sources. One way to determine the value of specific variable, voltage or current particularly, is to use the nodal or mesh analysis, which we have already described. So another way is to determine the contribution of each independent source to the variable and then add them up. The latter approach is known as a superposition. So we have two methods. One is using the earlier analysis in which we can calculate voltage or current by using the nodal or mesh analysis. But another method is that we can sum up the contribution of each individual source. So we'll first make take the contribution of one source, neglecting the presence of the other, and then we'll take the contribution of another source, neglecting the presence of the first one, and then add them up, add the two one. So the idea of superposition rests on the linearity property. That means the superposition principle is applicable onto the linear circuits. If we have a linear, non-linear circuit or a non-linear uh, component, we cannot use it. For example, current and voltage, they are related to the resistance linearly because V is equal to IR. If we have to calculate the power by using superposition principle, we cannot calculate it because power is a nonlinear term. Power will be V square by R or I square R, which is a nonlinear term in terms of voltage or power. The superposition principle states that the voltage across or current through an element in a linear circuit is the algebraic sum of the voltages across or current through that element due to each independent source acting alone. This is the nutshell of the superposition theorem. So the steps for the superposition principle is that we'll first turn off all independent sources except one source, find the output voltage or current, actually the current or voltage across the element which we are asked due to that active device or active source using the techniques already covered. We first have to deactivate all the sources except one and using the techniques that we already know, then to find out its contribution across the element. Repeat the step 1 for each of the other independent sources. So we'll do the same thing but now the other sources. Find the total contribution by adding the algebraically all the contributions due to the independent sources. Then we have to simply add the contributions, individual contribution we have to add. Let us try to use the superposition principle across this circuit, which is 4.6 figure. So in this case, we are asked to find out the V, that is the voltage across this resistor, 4 ohm resistor. So deactivating, in case of voltage source, we can make the voltage source equal to 0 by simply replacing this voltage source by a short circuit. Similarly, we can make this current source to be equal to 0 by simply replacing this current source by an open circuit. Is it okay? I think this should be very clear. So since there are two sources present, let V is equal to V1 plus V2, and where V1 and V2 are the contributions due to 6-volt voltage source and the 3 ampere current source. That means V1 is the contribution due to 6-volt voltage source and V2 is the contribution due to 3 ampere current source. So to obtain V1, we'll set the current source to 0. When we set the current source to 0, we mean we have to replace this current source by open circuit. We'll simply open these two terminals. So in that case, the circuit becomes this one. So here Okay, this circuit becomes this one. This is the open circuit. Open circuit of this figure. The remaining of this figure will be, there will be a series connection of 8 ohm, 4 ohm and 6 ohm resistance. So we're assuming a current I1 flowing in this circuit, and using the mesh analysis you can see that you can see that 6 is equal to 8i plus 4i, that is 6 will be equal to 12i. That is what here this has been written. 12i minus 6 is equal to 0, or 6 is equal to 12i, or I1 is equal to 0.5 amperes. Here this V1 will be equal to 4 times I1, that is this. So I1 is 0.5, that means V1 is equal to 2 volts. We may also use the voltage division to get the V1 by writing. It's 4 divided by 4 plus 8 into 6. 4 divided by 4 plus 8 into 6 is equal to 2 volt. In that case also we can find it out. We have already done it. Voltage divider rule, when two resistors are in series to a voltage source, the voltage across one resistor will be that resistance value multiplied with the voltage divided by sum of resistance, that we have done over here. To get V2, we set the voltage source to 0 as in 4.7b. You can see it over here using current division. So here we have to replace this 6 volt battery by a short circuit. So this terminal and this terminal are short circuited, and we get this circuit. So this current will be then divided into two circuits, circuit elements, 8 ohm and 4 ohm. We can simply use the current divider rule to get the I3, because we need to find out V2. V2 will be equal to I3 multiplied by 4. So I3 will be equal to, so current division rule will be equal to the total current multiplied by the other resistance divided by the sum of resistance. You can see total current is 3 multiplied by the other resistance, that is this resistance, because we are not calculating current through this resistance, we are calculating current through this resistance divided by the sum of resistance. It will be equal to 8 divided by 12, that is 2 by 3, 3 and 3 will cancel for 2 amperes. So V2 will be equal to 4 into V, that is 8 volt. Here also we have to be very clear about the polarities. Polarity is plus minus, here is plus minus. So simply V will be equal to V1 plus V2. Since polarity is same, it will get simply added. It will be 10 volt. So we can also use the technique of nodal analysis to find out. You will see that this will be again equal to 10 volts. So if you are asked to find out the power by using superposition principle, you cannot find out the power by using superposition principle. What you will do, you will first find out voltage or current through this and then find the power. So here, since we have calculated the voltage equal to 10 volt, we can calculate power to be equal to V square by 4. V square is 10 square, 10 times 100 divided by 4 is 25 watts will be the power consumed by this resistance. So you will try this circuit at home. This is almost a similar circuit, but the only thing is that there are three resistances and we have a current source in between the two meshes. Please try to do it at your home. Now Thevenin theorem. This is one of the most important and one of the most used theorem in electrical circuits. So what it does this state? It states that a linear two-terminal circuit, that means again this is also applicable to a linear circuit, can be replaced by an equivalent circuit consisting of a voltage source VTH in the series with the resistance RTH, where VTH is the open circuit voltage at the terminal and RTH is the input or equivalent resistance at the terminal when the independent sources are turned off. So what does this mean? It means if we have a linear circuit, linear two-terminal circuit like this, and it is connected to a load through these terminals A and B. So it means that this linear two-terminal circuit can be replaced by this type of circuit, which is a combination of or series combination of a voltage source VTH and resistance RTH. So what does this mean? What is VTH and what is RTH? So VTH will be, for this circuit, when we open these two terminals, we will calculate what will be the VTH over here without applying the load. Again, RTH will be the resistances that is seen between these 2 points when the load is thrown off or when the load is not connected. but all the independent sources should be turned off. That means current source should be replaced by an open circuit and voltage source should be replaced by a short circuit. That is what this circuit has been replaced by a Thevenin circuit. That is what is meant by the Thevenin theorem. The proof of the theorem will not be given here. Our major concern right now is to find out how the Thevenin equivalent voltage and resistance can be calculated. To do so, suppose the two circuits in the figure below are equivalent. Actually, these two figures, two circuits are to be equal if they have the same voltage current relation with their terminals. This is actually general rule that two circuits will be the equivalent of each other when their terminal uh, current and voltage relationships are same. We can say that the two circuits are equivalent. That means when we replace this circuit by this circuit, and when we have connected this load to this, you can see we have shown the current I here and the current I here. That means it is drawing the same current from this circuit and from this circuit. It means this circuit will be then the equivalent circuit of this circuit. For the same voltage, it draws the same current. Let us find out what will make the two circuits in figure equivalent. If the two terminals are made open circuited by removing the load, no current flows, so that the open circuit voltage across the terminal in figure A must be equal to the voltage source in figure B. That means when they are equivalent and when the load is not connected, the open circuit voltage over here and the open circuit voltage here should be same. That means the open circuit voltage will be VTH since the two circuits are equivalent. Thus, the open circuit voltage across the terminal as shown in the figure will be VTH. That is this. VTH will be equal to VOC. That is this. Again, with the load disconnected and the terminals open circuit, we turn off all the independent sources just to calculate RIN or RTH. Then put resistance or equivalent resistance or Thevenin resistance of the dead circuit. Dead circuit means when all the active sources are not connected. At the terminals in previous slide figure is must be equal to the previous slide because the two circuits are equivalent. That means this should be the Thevenin or equivalent resistance when we look into these 2 points towards this circuit. They should be equivalent. That is Thevenin theorem is very important in the circuit analysis. It helps us to simplify a circuit. A large circuit may be replaced by a simple circuit independent voltage source and a single resistor. That means a large circuit will be replaced by this circuit. This replacement technique is a powerful tool in circuit design and it makes this problem very simple. So finally, this IL, when we have replaced the actual circuit by the Thevenin circuit, you can see that this IL, that is the load current, will be equal to this VTH, Thevenin voltage, divided by RTH plus RL. This is now the series circuit. So VL will be equal to RLIL in RL divided by RTH plus RL into VTH. You can use the voltage divider rule as well. It will be equal to this. The voltage across RL will be value itself, value of the resistance itself divided by sum of resistance multiplied by this voltage, that is this. Now we'll try to use the same thing to find the Thevenin equivalent and to find something in this circuit. Find the Thevenin equivalent circuit of this circuit shown in figure 4.27 to the left of the terminal AB. That means we have to see this is a load circuit, load resistance. We have to find out the Thevenin equivalent of this circuit. Then find out the current through RL is equal to 6, 16 and 36 ohms. Okay. So what is the first step in doing this? We'll first open this load at terminal A and B. The circuit will be reduced to this circuit, and by doing this we'll first find out the values of RL, RTH. You can see when we have finding out the value of RTH, we have to deactivate all the sources. We have to replace this source by a short circuit and we have to replace this by an open circuit. When this is an open circuit, there will be nothing connected between this, and this will be short circuit. The circuit will be reduced to this circuit. So RTH will be parallel combination of these two plus this. This will be, then that combination will be in series with this. Total will be parallel combination of 4 and 12 plus this series combination of the combination of that plus this 1 ohm. So it comes out to be 4 into 12 divided by 16 plus 1. It will be 4 into 12 will be 48 divided by 16 will be 3. 3 plus 1 will be 4. This will be the RTH. So to calculate VTH, we'll use the mesh analysis over here and to find out the value of this. Or you can use directly uh, have this nodal analysis here to calculate VTH. And for my opinion, I think nodal analysis will be better because in nodal analysis we have only one unknown node, that is this node. Here actually we have to find out the voltage VTH. This VTH will be same as this VTH because there will be no voltage drop in this since no current flows over here. So when there is only one variable, nodal analysis would have been better, but here this book has used this mesh analysis. We can go through mesh analysis as well, because using mesh analysis here we have to find out two variables, that is I1 and I2. So I recommend you to find this VTH by using the Thevenin theorem. To find VTH, consider the circuit of this. Applying mesh analysis to the two loops, it will be 32 minus 32 plus 4 times I1 plus 12 times I1 minus I2 is equal to 0. That is this, by simply okay is equal to 1, and here this I2 will be equal to minus 2 amperes. So because I2 is a constant value, this 2 ampere is a constant value. Since we assume this to be I2, it should be equal to minus 2 amperes. So substituting this I2 over here, so we'll get I1 is equal to 0.5 amperes, and VTH will be the voltage drop across this resistor, that is 12 into I1 minus I2. So 12 into I1 minus I2 will be equal to, since minus I2 is 2, this is 0.5, is 2.5 into this, it will be 30 volts. So this is our VTH. You can see it, this has also done the same thing by using nodal analysis. Alternatively, it is even easier to use the nodal analysis, which I have just described to you. We ignore the 1 ohm resistance over here. Since no current flows through it, at the top node KCL gives at this node, that is this current will be equal to this current. Sorry, this is the incoming current, this is the incoming current, this is the outgoing current. So the total current over here will be equal to 32 minus VTH divided by 4, that is this, plus this current, that is incoming current, plus 2 is equal to VTH by 12. Here is only one variable, that is VTH. We can calculate it from here. So 96 minus 3 VTH plus 24 is equal to VTH. VTH comes out to be 30 volt. So this is our final circuit where VTH is 30 volt, RTH is 4 ohm, and this is a variable load. So what is the value of IL? IL will be equal to VTH divided by RTH plus RL. RTH we have calculated. This is 30 divided by 4 plus RL. So IL, so now we have to find out the value of IL when RL is equal to 6 ohm. IL will be equal to 30 by 10, that's 33 amperes. When RL is equal to 16, so IL will be equal to 30 divided by 20, it comes out to be equal to 1.5 amperes. And when RL is equal to 36, so 30 by 40 it will be 0.75 amperes. So if RL is equal to 4 ohm, you will see that this current will be equal to 30 by 8, that will be equal to 3.66 amperes in that case. As you will see in the next 2 or 3 slides, that will be very concerned about the value of RL and the value of RL when they are seeing what will happen to the circuit. So please try this. This is a similar problem. You can calculate the value of I by using Thevenin theorem. Simply disconnect this load from it. Calculate RTH between these 2 points. That will be series. And this is open circuit. This is short circuited. Series combination of these two, and then the combination of these two will be in parallel with this. That will be RTH. And when you open up this, you have to find out the VTH at this point. So you can use superposition theorem, you can use nodal analysis, or you can use mesh analysis to find out the value of this VTH. I'll recommend you not to go to mesh analysis because there will be some sort of problem over here. So that technique I haven't shown you how to calculate this, how to calculate some currents. Sorry, how to use the mesh analysis when the current is between two current sources between two meshes. Here the current source is between two meshes, so you just don't try that. You just use the nodal analysis or superposition theorem to calculate the voltage at this point. So Norton theorem, this is the home assignment. This is the dual theorem of the Thevenin theorem. You will do it on your own. It's very simple. It is given in the book which I have given to you. Now coming to maximum power transfer theorem. In many practical situations, a circuit is designed to provide power to the load. There are applications in areas such as communications where it is desirable to maximize the power delivered to the load. We now address the problem of delivering the maximum power to the load when given a system with known internal losses. It should be noted that this will result in a significant internal losses greater than or equal to the power delivered to the load. So when we are not concerned about the losses, we can use the maximum power transfer. If we are concerned about the losses, then we cannot use this, because when we maximize the power transfer, it also results in the maximizing the internal losses. Now, let us use the same circuit, that is the Thevenin circuit. And actually, this circuit is very useful in calculating the maximum power transfer. So the Thevenin equivalent is very useful in finding the maximum power transfer in a linear circuit that can be delivered to the load. We assume that we can adjust the load resistance if the entire circuit is replaced by its Thevenin except for a load as shown in the figure. The power delivered to the load is given by this P is equal to I square R, where I is the current flowing through this circuit. That is equal to VTH divided by RTH plus RL, because this will be the current. Square is this square into RL. When you change the load resistance from 0 to infinity, when RL is equal to 0, this load comes out to be equal to 0, or this power comes out to be equal to 0. When RL is infinity, so this is infinity square, so it comes out to be again 0, because when you uh, multiply this RL to this, you will get, or divide RL in numerator and denominator. What you will get VTH divided by RTH divided by square root of RL. Sorry, VTH divided by RTH divided by RL plus 1 divided by, sorry, not 1 divided by RL, because this will be RL square, it will be RL. When RL is infinity, this comes out to be equal to 0. When it is 0, this is 0, this is 0. This term will be actually equal to VTH by RTH, but this 0 makes it 0. When it is infinity, you can divide RL to numerator by denominator. So this will be VTH square divided by RTH divided by RL plus RL. This RL will make it to infinity, and whole term will be equal to 0. That means in between RL is equal to 0 to RL is equal to infinity, because it started from 0 and again comes to 0. There must be some maximum in between these two, and we need to find out this maximum RTH, where maximum value of RL, where maximum power is transferred to the load. So how this can be done? Where is this? We notice that the power is small for small and large values of RL, but maximum for some value of RL between 0 and infinity. I have just discussed it. That's why I just gone through these points. We now want to show that maximum power occurs when RL is equal to RTH. So what I mean to say is that I haven't discussed it. The maximum power will be transferred to the load when this RL is actually equal to the internal resistance, that is RTH. This is known as RTH maximum power transfer theorem. So the derivation is like this. I'll first read the statement again. Maximum power is transferred to the load when the load resistance is equal to the Thevenin resistance as seen from the lower, that is RL is equal to RTH. So the equation which we have just written, that P is equal to this VTH square divided by RTH plus RL into RL. So by varying RL, we'll differentiate this power equation by RL, or with respect to RL, and we'll equate that to equal 0. We'll see what will be the relation between RTH and RL. So by differentiating this equation with respect to RL, we'll get this. Keeping this VTH as constant term, this numerator, it will be as it is. Sorry, numerator is RL. The differentiation of RL will be 1 minus, this will be RL. The differentiation of denominator will be equal to 2 times RTH plus RL. That is, this minus is there because of the formula of differentiation of U by V, and then numerator will be squared. That is RTH plus RL square into square will be raised by 4. Now by opening this up, this will be equal to RTH square plus RL square plus twice RL RTH. This will be minus twice RL RTH minus twice RL square. This twice RL RTH and the twice RL RTH will be cancel out. This is minus twice RL square. This is RL square. So RTH square minus RL square will be equal to 0. Okay. So in that case, RTH and RL will be equal to, or you can see from here, it has taken this RTH plus RL common. Here also, this it remains RTH plus RL minus 2RL this, and then RTH plus RL be cancelled from this factor. There remains only this cube root, sorry, cube. So total will be RTH plus RL minus 2RL, it will be equal to RTH plus RL minus 2RL will be equal to 0. That means RTH minus RL will be equal to 0, which means RTH should be equal to RL. So in that case, when RTH will be equal to RL, so Pmax will be equal to this. When RTH will be equal to RL, this will be equal to 2 times RL or 2 times RTH. So the square term will be VTH divided by 4 RTH square. This RTH and RTH will cancel out. So in that case, it will be equal to V square TH divided by 4 RTH. So let us try to use the same concept and try to find out the maximum power that is transferred through this resistance R. So first we'll convert this circuit into the Thevenin circuit. While converting this into the Thevenin circuit, first we'll calculate RTH between point A and point B. So when this is done, so all the active sources have to be deactivated. This will be replaced by an open circuit. This will be replaced by a short circuit. So the circuit will be reduced to this circuit. So here 6 ohm and 12 ohm resistance will be in parallel. Their parallel combination will be equal to 6 into 12 will be 72 divided by 18 will be 4, and then the series combination of these three, 4 plus 3 plus 2, that will be equal to 9 ohm. That means the RTH will be equal to 9 ohm. To calculate the value of VTH across this, that will be the voltage across this. So we'll use the mesh analysis. I2 will be equal to minus 2 ampere minus 12 plus 18 I1. 6 plus 12 is 18 I1 minus 12 I2. That is the combination of, common resistance between these two will be equal to minus 12 I2 is equal to 0. Solving for I1, we get I1 is equal to minus 2 by 3. Applying KVL around the outer loop, that is over here, because here is not resistance, so that we can multiply that resistance by current, we get here is the voltage source. So outer loop to get VTH across terminal A and B, minus 12, that is actually this loop. This voltage minus this voltage drop minus this voltage drop will give us this voltage. So the voltage drop across this, so it has actually used this voltage minus this voltage drop minus this voltage drop minus this voltage drop is equal to VTH. So minus 12 plus 6 I1 plus 6 I2 plus 2 into 0 plus VTH, because we are going from plus to minus, is equal to 0. So here by solving, VTH is equal to 22 volts. For maximum power, we know that RL is equal to RTH. We don't have to find out this RL. So RTH we have already calculated, that's equal to 9 ohms. So it comes out to be this. So the maximum power will be equal to Pmax Vth squared over 4RL, that's 22 squared by 4 into 9, that is 13.44 watts. In this way, we'll be able to calculate the maximum power. We have to first convert this circuit into the Thevenin circuit, and then RL will be equal to RTH for maximum power transfer. Thank you. I think this will be enough for today. I will stop over here. Thank you.